Hello, welcome back. This is the lecture series on foundations of data science and machine learning, and through life experiences. So this in this lecture, we're going to talk about the mathematics of love. Specifically, we're going to talk about this thing called the Eigendecomposition. Now, I'm Professor Wu. Let's get started. So first, by now you have taken the first exam, so you first thing we're going to review is how to take determinants. You need to remember how to calculate determinants. This is a 2 by 2 and this is a 3 by 3, so if you took the exam you should remember. Now then, your first exercise, refresh your memory. Take the determinant for this matrix. Okay? Pause the video, give this a try, and you should be fine once you get it. Okay, pause the video. This is the solution. Now, if you have extra time, right? If you have extra time, you could work on this. If you do another one, pause the video. You should it should be pretty easy. Okay, here's the solution for the second one. Okay, now we're ready to move on. The mathematics of finding yourself. Finding yourself. Okay, we previously learned that we all have various characteristics, and these characteristics, each characteristic can be modeled as a vector, right? So we can model ability, tools, basically anything can be modeled as a vector. And to describe a person, right? Here's an example. You can measure them by their kindness, how passionate they are they career goal oriented, intelligence. So, I mean, you can come up with a list. So, with a giant list of vectors, they form a basis for you that describes you, right? So, a person is a combination of these characteristics, right? Therefore, if we put all these vectors together, we construct some kind of matrix. So, in a way, we can describe each and every one of us as a matrix, right? That's a combination of different vectors. And if you think about it carefully, like if we try to model everything about you, right? Everything imaginable, every thought, every feeling, every idea, right? Well, how big would the matrix need to be, right? If you think about it, every single memory, every thought, every idea, and the entire history that encompasses who you are. Like you can imagine, this will be a gigantic matrix. Right? Therefore, with the gigantic matrix, each and every one of us is like a universe um, unto ourselves. And therefore, it's very difficult to understand, to truly understand someone. You can imagine if I give you a gigantic matrix, I don't know, 10,000 by 10,000, maybe even bigger than that, a million by million. How long would it take for you to memorize the entire matrix, right? So if you meet somebody and a person is really, really complicated, like a 10,000 by 10,000 matrix, to know this person, you would know every single value, right? And that could be very, very complicated because we are all really complicated beings. Therefore, it's sometimes we're kind of being unfair to expect us to just understand us. And yet, in life as well as in love, we all seek to be understood, right? We want people to know what we're talking about. And being misunderstood, if we're constantly being misunderstood, it kind of sucks. It's not that fun. So, so like it is within this feeling of being understood that it kind of help us no longer feeling so alone, right? Being understood is heavily related to the feeling of being alone or not. So from this, we see like an inherent dilemma. One, we want to be understood, but we're very complicated. And it takes a lot of work. It takes a time and work to try to understand us. And this is where self-doubt comes in, where like, can we find someone? Is there anyone out there willing, even willing to put that much effort for us? Right? We feel so complicated. Who's gonna put the effort to understand us, to really connect with us? Right? So this right here is an issue. We're too complicated for others to understand. So how do we humans normally get around this dilemma? Well, to understand someone, we don't really actually need to memorize the entire matrix. The matrix is really big, but if you remember, right, if we break a person down into components, we all have these essences about us. That's core essences. And if we remember that our matrix, right, consists of basis vectors. And what is about basis vectors that I've taught you guys? That is, there are a lot of redundant vectors. So you may have like 1,000, a million basis vectors, but the true dimension might be significantly smaller, right? And the true dimension is basically your orthonormal basis vector. So if we basically, instead of looking at all your basis vectors, v1, v2, v3, what if we can convert this into your orthonormal basis vectors, which is much, much smaller. It's much smaller. And if we understand your orthonormal basis, we don't really need to memorize every single one of your basis vectors, which could be like a million of them, right? And this idea leads us to this theorem called the spectrum theorem. Spectrum theorem. So the idea of spectrum theorem is really easy. Let's say we have a person, right, represented as a symmetric matrix A. So we have a matrix A, and this represents a person. And the spectrum theorem says that we can break down a matrix into the summation of its core components, core essence, right? It contains core essence vectors. So there are a bunch of vectors that represent your essence, and then values that represent them. So how does this work? It's saying that this matrix A, if you take your first core essence, multiply by its outer product, so this creates a matrix. So this matrix is come from your first core essence vector multiplied by some value, right? And then you have another essence about you, something that's about you, the second vector. And then, so you can see you have these core components of who you are. And these core components ultimately reconstructs this matrix of like the totality of who you are. And it turns out that if you find these core vectors, like core essence vectors, that is your orthonormal basis. That is your orthonormal basis. Okay? So this matrix, who you are, is a summation of your core essences. And this is a very convenient way because we don't need to memorize the entire matrix. We just need to recognize what are the core essences about a person, and that basically encompasses the person, right? Why does focusing on the core essence much easier to understand someone? Well, if you want to understand the usefulness of just looking at core essences, well, let's look at an example. So this is a matrix, and then this is the core essence: 1, 2, 3, 4, 5, 6, and all the way to 10,000. Now, if we look at the coefficients in front of them, notice how from 6 all the way to 10,000, these core essences do not contribute because it's 0, right? So it does not contribute. So they're core, well, they're not. They don't have to be exactly 0, but they could be a tiny number, right? And these numbers do not contribute because if you add like 0, well, this can be gone. You can reconstruct the original matrix. So, so basically, if we look at these values in front of it, these are the core essence values. Like how important is each core essence, right? This tells you how much it's used to reconstruct the matrix A, which is who you are. So just by looking at these numbers, notice how from 6 to 1,000, 10,000, these are all zeros. So we don't really need to pay attention to this. right? That already cuts out a lot of vectors we don't care about. And then if you look at from 4 and 5, notice how small the value they are contribute to your ultimate matrix. Therefore, if we just skip the two of them, it also doesn't really matter that much. And in the end, if you just know the three core essence of a person, it doesn't have to be three, but like you can imagine, you have like some people have 10, different people have different numbers. But if you just understand the core, then you don't need to memorize the rest of the vectors, right? Three vectors is much easier than 10,000, right? So, so in mathematics, these core essence vectors, v1, v2, v3, in mathematics they're called eigenvectors of a matrix. So, the core essence of who you are the matrix, is called the eigenvector, and these values that tells you how important each eigenvector is are called the eigenvalues. Okay, so the mathematics term, these are the key mathematics term you would need to recognize, and you will map them based on the story I'm telling you, is that the eigenvector, each one of them, is essentially used to reconstruct who you are. So those are the core essence of who you are. And the eigenvalues tells you the importance of each core essence. Okay, eigenvalue, eigenvectors. Let's play with this idea a bit. Right? Let's say a person has the following matrix right here, and these are the eigenvectors and eigenvalues. These are the eigenvalues. Now, remember this was the spectrum theorem, right? So a person is constructed with their core essence. So these are the questions I want you to answer. Use Python. You want to pull out the Python and see if you can calculate, double check that the eigenvectors are orthonormal. So that's the very first thing. Remember, I told you that the core essence happens to be orthonormal basis. So double check that, which requires you to do V transpose V equals identity. Then use Python to verify the spectrum theorem. So if you add up all three core essence, it should reconstruct the original matrix. And then notice how the eigenvalues of the third one is tiny. So don't use the third one. Ignore the third one and simply add up two of them. If you ignore this, can you use this alone to approximately reconstruct the matrix? Okay, so I have the solution here. You can take a look when you're done. Pause the video, and we are going to continue. All right. So now that we understand our core essences are the orthonormal basis vectors of who we are. Like once we know the orthonormal basis, remember they are orthogonal and normalized, and they span the exact same space as the vector space. So the natural question is, well, I told you previously, you have a bunch of basis vectors, and we want to find the orthonormal version, right? So the natural question is, how do we find it, right? And then it turns out that, continuing with our story, if we find it by finding our soulmates. So if we find our soulmates, it turns out that it gives us the eigenvectors, which is our core essence. So our core essence and the idea of a soulmate in this story basically are tied together. All right, so identifying the core essence does make it easier to understand someone. It does make it easier. Unfortunately, just because we can reduce thousands of vectors into just a couple, the process of identifying someone's core essence is still difficult, right? Let's say you have three vectors, but each vector is still like 10,000 length long, right? That's still difficult to do. So it's easier, but it could still take years for you to really get to know somebody, right? And I mean, in fact, there are a lot of married people that they marry for many years, and they realize they don't really know each other. Knowing, spending time with someone still takes a long time for you to really understand somebody. This is where we're going to introduce the idea of a soulmate. For this story purpose, we're going to mathematically define, that we define a soulmate as the very, very rare case where a person shares this identical eigenvector. right? So if someone essentially has the same essence as you, right? In other words, the two of you share the same essence. In these cases, when the eigenvectors interact with the matrix, right? The when your eigenvector, so that if someone has this essence, when this essence interacts with you, the gigantic matrix A doesn't look like a matrix anymore, right? It actually doesn't look complicated at all to the eigenvector, right? That's the special property. The eigenvector doesn't see you as complicated. Instead of the complexity of millions of numbers in your matrix, your essence, your essence, when you're interacting with someone with that same essence, simplifies who you are. They can just understand you immediately because you don't look like a matrix. To them, you just look like a number. That's all. Like, so you're a matrix with millions of numbers, but they don't see that. They see a very simple number, just one number versus 1 million, right? And for that reason, it's much easier to understand you if we've reduced the complexity down to one, right? So, but again, very, very rare case, very rare case. Well, when that happens, this magic happens where they just get you, right? Let's look at a more concrete example. Let's say we have this matrix A, and then I calculated ahead of time these two vectors. So these are the eigenvectors, right? These are your core components, core essence, and this one is not. Okay, so what happens? Well, if we take the matrix and interact with the core component, so I think the first one is 1, -1. So look at this one. Notice how when we multiply the vector by the matrix, it is equivalent to the vector, original vector, multiplied by a number, right? So the vector, when it sees this matrix, it doesn't see a matrix. Like this matrix is small, but imagine this matrix is like a million by a million. That's a gigantic matrix. And instead of seeing the matrix as a bunch of numbers, the eigenvector only sees a number. Right? So this example was for this. Right? So he sees a number. In other cases, over here, that's another eigenvector, so different core component of yours. Notice how when you multiply this vector by the matrix, so when there's an interaction between them, similarly, it's equivalent to the same vector multiplied by a number. So notice how this vector sees the matrix as a number. Similar here, right? They're mathematically equivalent. So, so these two cases are cases where you have eigenvectors. But here's the third case that's not. Notice that when we multiply by 1, 2, well, it's equal to 4, 4, which is nowhere near 1, 2. So this is actually changing the vector, and therefore, when it's changing the vector, then then it doesn't view it as a number anymore. For this vector, you need the entire matrix to basically get the output. Whereas for this one, you don't really need the matrix anymore. You just need the number. Similarly here, for this vector, you don't need the matrix. You just need the number. And you'll get the result of the interaction. And this is what I mean, that when you run into someone that has the rare case that they have the core essence, and you are interacting with that core essence, they immediately can reduce all the complexity of your matrix. And instead, they get it immediately because they see the number. So just one number versus the whole matrix. This right here kind of gives you a more concrete example of what I mean, that when you are interacting with someone's core essence, right, that happens to match yours. So if we go back, I'm going to define the idea of a soulmate is the rare case where a person happens to have the identical eigenvector, which implies that you guys are basically sharing the same like essence. Like you guys came from the same source, right? All right. If we continue with this analogy, right, someone with the same eigenvector, right, possesses the same core essence, right? That's why they understand you so well because you guys emerged from the same like primordial source. And based on the spectrum theorem, people who share the same eigenvector emerge from the same source. So no matter how complicated you may appear to others, you are always easily understood by your soulmate's eigenvector. So you're easily understood by the eigenvector because you're ultimately just a number. You're not a complicated matrix, you are just a number, right? So, and when you're just a number, the number that they see, right? So the number they see is called the eigenvalue. So A, if you have a mate, or what do I say over here, right? So right here, when your eigenvector multiply that by the matrix, they see a number, right? They don't see a matrix, they see a number. And this number that they see is your eigenvalue. Okay? So your eigenvector is the soulmate, and when they look at you, they see a number instead of matrix, and that number is called the eigenvalue. Okay, so therefore, mathematically speaking, we can write this out. The definition of eigenvalue and eigenvector must satisfy this equation, right? If it's an eigenvector, the vector multiplied by a matrix is the same as the vector multiplied by some number, which we call the eigenvalue. So this right here is the key definition you need to remember. Key definition. Key definition. Okay. So the whole story is for you to really remember this specific definition because the vector doesn't see a matrix, the vector sees a number. Okay? And our goal today is basically continue to build on this and see how do we go about finding the eigenvalues and the eigenvectors given your characteristic matrix, right? The matrix that describe who you are. Okay, so let's continue. So how do we find eigenvalues? Well, to find eigenvalue, we start with the definition where we have a vector and the vector v multiplied by some number is the same as the vector v multiplied by matrix. Okay, so we start with the definition and then we move it over here. So it's AV minus lambda v. Now, this is an identity matrix. So v times I is just equal to v, right? So this is the equivalent. The reason why we do this is because we can now pull the v out, which give us this equation. Once we pull the v out, this means that if the size of this is equal to 0, then we have the problem solved. So we just need to identify what lambdas to use that will give us a size of 0, right? So remember, how do we find the size? We find the size of the matrix using the determinant. So the determinant is one of the standard ways, right? So if we just look at this part, if the size of this is equal to 0, then it will satisfy the definition. So we just find the determinant of this. And we want the determinant so it's equal to 0, which will allow us to satisfy the 0. Okay, so to find the determinant of this, if it's a 2 by 2 matrix, remember we just do this to find the determinant. So, no, 2 by 2 we need to have the matrix A minus lambda identity, right here. And then we want to find the determinant. So we just calculate out. We know A, we don't know lambda, so it would be A1 minus lambda, and then A22 minus lambda, and the 0 here, so it doesn't change. And now we find the determinant of this. Well, the determinant is this times this. right? The reverse alpha, which then looks like this, equal to 0. Okay, well, then that kind of solves the problem. If we find the lambda such that the result is equal to 0, then we essentially know the eigenvalues, right? This right here, this expression is called the characteristic polynomial. Characteristic polynomial. So this is it. Actually, you find you start with this definition, and it leads you to the characteristic polynomial. Once you solve it, the problem is solved. Right. So let's give this a try. Let's say you're a matrix. This is the matrix, and since this is a 2 by 2, this is a simple case where you have two eigenvectors and two eigenvalues. So let's see that if you can find the eigenvalue. Okay. So pause the video. You don't need to find the eigenvector yet. We'll just work on the eigenvalue. Okay, let's continue. This is a solution. All right, so given each eigenvalue, we can now, for each eigenvalue, we can find the corresponding eigenvector. All right, you need to know the value first, and once you have the value, you can find the vector. And the eigenvector are your soulmates, or where that contains it contains like your essence, right? So let's find your soulmate. Well, once again, we start from the definition of eigenvalue, eigenvector, your soulmate, and then what we want to do is we now know that from the previous example, we found that the eigenvalues are 1 and 3. So those are the eigenvalues. Now, for the eigenvalue lambda 1, there's a corresponding eigenvector, right? And then lambda 2, there's a corresponding of eigenvector. So let's start with this one and try to find your first eigenvector. And it's actually pretty easy. We know lambda, right? So we now know lambda. So we can now once again move this over here, and we can pull out V1. The difference between now and before was that now you know this number. Therefore, this is a known matrix. This is a known matrix. And we need to find V1. This right here implies that you simply need to find the null space for M. Right? If you find the null space, then the problem is solved. So now you may remember this looks very, very similar to the mathematics of friendship. Right? The mathematics of friendship, if you remember, the friendship matrix is between two people, V and U. And then we're trying to find the null space of F, right? So over here, it is very, very similar. Very, very similar. We're also finding the null space. But this time, we're not finding a null space between two friends. Like, we're finding somebody who ultimately just will understand you automatically. Right? So the result is, if you can calculate this matrix here, M, the null space is essentially will give you the eigenvector. Okay? The eigenvector, that is the person you're looking for. So if we do a quick example, right, over here, remember for lambda 1, right? So let's say you have lambda 1, and you're trying to find the eigenvector for lambda 1. All right, give it a try. Take what I just told you. I'll pause the video, and I'm going to continue. Over here is the solution. And then once you're done with that, try it again. So you remember you had two eigenvalues, 1 and 3. Now for the 3, now try to find its corresponding vector. I pause the video. I'm going to continue. Now, it's always a good idea to double check your work. Once you've found the eigenvalue and the eigenvectors, what you can do is you can just take it and actually multiply by your matrix. And then you will see that, okay, the eigenvalue checks out and the eigenvector checks out. So you should see this relationship when you're testing it. Right, normalizing eigenvectors. Now, once you get an eigenvector like this, eigenvector, what we like to do is, right now, they are orthogonal. Orthogonal. By default, like when you find eigenvectors, they are always going to be orthogonal. But however, they are not orthonormal. Remember, we really, really like orthonormal bases because for projection reasons, it's not really doable. So what we do is we normalize them all into length of 1. Therefore, we take this one, normalize length of 1, which will be just divided by 1 over square root of 2. Similarly here, now we have both of them into a 1 over square root of 2. So now we have the orthonormal bases once you normalize them. And what we like to do is to stack them into a vector. Right? So we stack them, stack them. Okay. Now, if you want to find eigenvalues and eigenvectors in NumPy, it's actually pretty easy. Let's say you have a matrix here. And then if you simply type linear algebra for eigenvalue, and then it will give you the lambda right here, 3 and 1, and then it will give you the eigenvector. Okay, so the way it's set up is this is the eigenvector associated with lambda 3. This is the eigenvector associated with 1. Okay. All right. Now, what is really interesting is that let's say you are dating somebody and you are not the soulmate, right? I mean, it's very, very unlikely that you will ever date anyone who's your soulmate in your lifetime. However, let's say you're not. So what is how does the interaction work when you are not? Okay. So right here I wrote the code. So this is that matrix. And then remember, this was that vector that was not the eigenvector, not. And when it's not, what I do is what happens when you have repeated exposure. So this is the core essence of like the person you're dating. This is who you are. What are you doing? What are you trying to do? Okay. So if what will happen if every single time your partner is exposed to you, and this gives you a changes your partner slightly. Okay, so I'm going to put it in a loop 10 times, and then what I do is I basically just keep multiplying u by a. All right, that give us the resulting u, which I make sure I normalize. So basically I'm going to do u times a, right, and then u times a again, u1 u2, then u times a again. So what happens when your partner gets repeated exposure? Well, your partner starts off as 1 1 2, right? So it starts at 1 2. After one step, you change the partner slightly. 2 step, 3 step, all the way to the 10th step. Okay, so it seems to me that your partner is converging you, changing you towards this value, right? Notice how every single step is getting closer and closer and closer towards this. So in this particular case, your partner is changing you into somebody, like with certain kind of a core essence that reflects this. And what is this? Well, let's take the eigenvalues of eigenvectors of A. Notice how this right here is one of the eigenvectors. So what this observation tells you is that when you are interacting with someone, even if they're not your soulmate, through repeated exposure, you're actually slowly changing that person into your soulmate. If if the person's willing to make adjustments, then they will ultimately understand you eventually, right? It takes a lot of iteration. But that is really interesting how like we are always changing somebody. We're always trying to change our partner into somebody we ideally will want to be like, and that may or may not be successful, but the math here is quite interesting if you kind of look into it. Okay, another interesting thing is only square matrix can be used to find eigenvectors. Later on, I will teach you guys how to deal with non-square matrix. But one quick idea is if you have a matrix A and it's not square, you just multiply A transpose A, and this will always be square and symmetric. All right, and you will have the same basis. It will span the same space. Span same space. So even if you don't start off with like a square perfectly symmetric matrix, you can do a quick conversion and then it will be good. Okay? Okay, so previously we looked at the spectrum theorem. The spectrum theorem basically says that the matrix A is a combination of your eigenvectors v1 v1 transpose lambda 2 v2 v2 transpose, right? Now we like to write this in a compact way. Right? Now if we were to combine all the eigenvectors as columns here, and then the eigenvalues are here. So the first column is associated with the first eigenvalue, second column is associated with the second eigenvalue, so that you have matrix V and the eigenvalues. So this right here can be rewritten into this form. It's saying that A is simply a decomposition of the V matrix times sigma, which is all your eigenvalues, diagonal, times V inverse. This right here is a different version of the spectrum theorem. And this is called diagonalization. Diagonalization. It's saying that you are constructed by the components, your components. If you rearrange this, you should be able to get this back. This is just a matrix version of this. Now, this is general. A doesn't have to be symmetric, but if A happens to be symmetric, it's even better, because when it's symmetric, we know then it's normalized. Then V transpose is equal to V inverse. So instead of V sigma V inverse, it's V sigma V transpose. Okay? So it's saying that you can be broken down this way or this way, depending on whether the matrix is symmetric or not. And I wrote a little bit of code here. You can see how when you take V sigma V transpose, it reconstructs the original matrix. So you can see, like, through your core essence, eigenvectors, you can use them to reconstruct yourself. All right, it takes a lot of practice to combine all these ideas together. So let's say we model U as this matrix. Now give it a try and see if you could. Now notice this is not symmetric. Not symmetric. All right, give this a try. Answer these questions. Pause the video so you can answer them. And over here is the solution. Okay. Over here as well. I think that's part of the solution. Oh, I think that's also part of the solution. Here's the code portion of the solution. All right, let's do another one. Here's Josh. This is Josh over here. And here's Josh's matrix. Let's see if you can find the eigenvector by hand. All right, pause the video. I'm giving you the solution here. Continue with the solution. And that's it for today. So hopefully that was useful. Like we use the idea of love to kind of help us like remember the definition of eigenvalues and eigenvectors. Now, ultimately, the key relationship that you need to remember is that the vector, eigenvector, it doesn't see you as a matrix, it sees you as a number. Once you remember this equation, everything else could be kind of re-derived based on this. Okay? I will see you in the next lecture.